and let's have at it. What can I help you with?
So I think we were going to work on non-ideal gases.
Oh, okay. So let's look at non-ideal gases. So I'll just give you some little background here. Let me do a change share. And each book has a different take on ideal gases as far as the reason why you have a formula for ideal gases versus non-ideal gases.
Mhm.
And it's not really non-ideal gases, it's really real gases. So an
Right.
ideal gas is ideally how it behaves. And we know that models are always simpler than the reality. They try to make it simpler so that we can work with it, right? So it turns out that there is no such thing as an ideal gas. Okay, but what are the conditions that would help you to have more of an ideal gas than less of an ideal gas? So one of the things that you need to know about is called STP. That stands for standard, temp, and pressure. Now you would think that standard temp and pressure would be the pressure of the atmosphere, which it is. So the pressure is 1 atmosphere. And notice I don't have 1.000. It's 1 exactly. This is a definition. We're defining STP as 1 atmosphere exactly, okay? The temperature is defined as 0 degrees Celsius exactly. So, that's kind of interesting that the standard temp is 0 degrees Celsius instead of, say, room temp. But I don't know why they chose that, but this is the way it is. Now, when we add 273.15 to that, we get 273.15 K, correct?
Mm-hmm.
Now, since the 0 is exact, and since the addition of 273.15 is only good to the 100th, this is only good to the 100th, or another way to say it is 5 sig figs, depending on how you use it, right? If we're going to add this to something, we say it's good to the 100th. If we're going to multiply it, we say it's good for 5 significant figures. Okay, so standard temp and pressure are the temp and pressure at which a gas would be more ideal. So these are the ideal pressure and temp for gases. So that means if you have a higher or lower pressure, it would be less ideal. And if you had a higher or lower temp, it would be less ideal. Fair enough?
Yeah.
Okay, so that's real easy. So why do gases not behave ideally? Why do they differ? Why do they, what makes them behave in a real fashion? So I'm going to put real gases. So do you remember the ideal gas, or the one of the kinetic molecular theory of gases is that the space between the particles is really big and the particles themselves are small?
Yeah.
And so here, for real gases, the real volume is less than the ideal volume. So let me show you what I mean by that. If this is your gas, and this is the ideal volume, and this container here is supposed to be the same container, same size, right?
Yeah.
So I'm going to put ideal on the outside here. So you can see there's a lot of space between particles, correct? Now, let's say that we turn all those particles into a liquid. So they fall to the bottom of the container and fill up the bottom. They're not going to fill up the whole container because gases are mostly space, right? So up here we have the space between the particles. Down here we have the particles themselves. Well, I'm going to kind of circle this right here. That's the real volume that the gas particles have to monkey around in.
Okay.
So do you understand now what I'm, by this drawing, that the real volume is less than the ideal volume?
Yeah.
Okay. So the kinetic molecular theory of gases, like you say, like it says, it's a theory. It's not a law. You with me?
Yeah.
It's how we think about it for how it behaves. Now, what are the differences between these two values? And the answer is not very much. It's probably less than 1% difference. So in a chemistry sense, in a science sense, if you're within 1% of the real value, you're like, yeah, this is great. Okay. Now, the other thing that we talk about is the pressure. The real pressure is actually greater than the ideal pressure. It's the opposite. Do you see that?
Yeah.
Okay. So if we look at the pressure ideal, this is something that we're measuring, right?
Mhm.
And the particle hits the wall and we get the ideal pressure. And it bounces off, right?
Right.
Okay. Well, the idea here is that we have non-elastic collisions. They're not elastic. Elastic means when you hit the wall at 100 miles an hour, you bounce off at 100 miles an hour. That's not the case. So what happens here is that the pressure kind of lowers when it bounces off because it hits at 100 and it goes off at 90. So the real pressure of this particle after it's hit the wall is less than what we consider to be the ideal pressure.
Okay.
Okay, so here the idea is that this is because, I should write little things here. This is because, I know I'm changing back to this. This is because gas particles have volume.
So yeah, it's taking account for the
And that
particle.
takes account, and this is because gas particles are sticky. They stick together. And we know they stick together because of something called van der Waals interactions, which we haven't talked about yet. But you can understand that some molecules are polar and some are nonpolar, right? So definitely when they're polar, they can stick together because they will have that opposite attraction, right? So if they have that sort of attraction, they can't bounce off elastically. So the ideal is going to be less than the real. So when we look at real gases versus ideal gases, we have PV equals nRT, right?
Yeah.
For the real gases, we have something called the van der Waals equation. And this is an equation that I would not bother writing down on my note card or memorizing.
Okay.
So we already know that this is ideal. So I'm going to put a little I here for ideal.
Okay.
So now we're going to have the pressure real, volume real is equal to nRT. So remember that the real pressure is greater than the ideal pressure, right?
Yeah.
So that is written this way: pressure plus A N over V squared. And this is really the real pressure. So this would be the ideal. And we add this little extra to it because the ideal is less than the real pressure. Now remember, our real volume is too large, right? The ideal volume is too large. So
Right.
what do we have for the correction here? It's minus Bn and then equals nRT.
Okay.
So N is the moles of gas, V is the volume of gas, and A is a number that depends on the identity of the gas. What do you think B is?
It also depends on the gas.
It's a number that depends on the identity of the gas.
Okay.
So what are the factors that influence B? We'll start with that one first. So remember, we're subtracting B times N. And doesn't it make sense that the more moles you have, the more liquid you're going to have at the bottom and the less volume you'll have?
Mhm.
So that's why we have the N in there. That's a pretty evident. So what does B depend on? B depends on the size of the molecule.
Right.
So larger molecules have bigger B's and smaller molecules have smaller B's. Okay, so B depends on the identity of the gas, and we're just going to say size.
Right.
And really, we're talking about volume, correct?
Right.
Not mass, but volume. Okay, now what is going to influence this? Well, naturally, the more moles of gas you have, the greater the pressure they will have because you have more molecules hitting. You with me?
Mhm.
But naturally, the larger the volume, the less often they hit, so the smaller the pressure. So that's why you have both of these in here. So what are the factors that influence A? Well, it is kind of the size of the molecule, but there's another factor. Two factors that affect how well a molecule sticks to another molecule. The two factors are size and polarity. So it turns out that big molecules stick together better than small molecules if they're nonpolar. So a Br2 would stick to another Br2 better than a Cl2 would stick to a Cl2 because the bromines are larger.
Okay.
But also, the more polar a molecule, the better they'll stick together. So two H2O molecules are very polar compared to two ammonia molecules, which are also polar, but not as much. And they're about the same size. So you would expect to have a higher A value for water than for ammonia. So here, it depends on the identity of the gas. We're going to say size and polarity.
So A and B are values we could look up if we wanted.
No,
No?
because I'm not going to ask you I'm not going to give you a problem on the test that says here's an A and here's a B, calculate it.
I just mean it like if for our own personal, like
Oh
if
yeah,
the
you could
values
look
are
at
out
A's and
there
B's.
somewhere and we could
Yeah.
look it up.
Our book even has some A's and B's.
Okay.
And since you've asked, let's go ahead and take a look at those A's and B's.
Okay.
See, this is the problem with asking questions, Charlotte. Sometimes you get answers. All right, so here are some A's and B's. Now, we're going to ignore the units for the values, okay? But remember how I said that the B values are basically going to be dependent on the volume of the particle?
Right.
Do you see that the helium particles have a smaller B than argon? And we would expect argon to have a larger volume than helium because it has a larger mass. They're both in the same group, and they get larger as you go down the group, correct?
Yeah.
Here, you can see that hydrogen actually has a greater value than helium.
Yeah.
Even though hydrogen has a smaller mass, but we have to remember that hydrogen, we're looking at two of them together, right? So we might actually expect H2 to be twice the value for helium, but it's it's the surface area. And when you combine the two hydrogens together, the surface area where they're touching doesn't count as part of the surface area that makes them sticky.
Okay.
So that's why it's not twice the value. So it's really hard to conceptually say, okay, how do I calculate these? You don't. You experimentally determine them.
Yeah.
Okay. I don't know of any program that allows you to experimentally calculate them using the program. You determine them by testing them experimentally. Now look at this molecule here. Let's see. The biggest molecule here is definitely the Cl2 because those atoms are very large, and you see it's a 0.0562. So it's got a pretty big B.
Yeah.
Okay, now for the A values, if we look at helium and argon, can you see that the argon has much greater surface area than helium?
Right.
So that's why they stick together better.
Okay. Larger
Okay.
mass.
And then over here, if we take a look at this, you see how the Cl2, we would expect that to have a huge surface area, and it sticks together pretty well. CO2 has a pretty big surface area also, not as big as Cl2. And do you remember the Lewis structure for CO2?
Yeah.
Completely nonpolar, right?
Yeah.
The Lewis structure for Cl2, completely nonpolar. So here we're just looking at surface area.
Okay.
Now look at this guy here. This guy only has 1 oxygen and 2 hydrogens. Its surface area definitely has to be smaller than Cl2 or CO2, right?
Right.
But it's got a really huge A. Why?
Polarity.
It is a very polar molecule. So when they run into each other, they can stick together and kind of sap energy away, so to speak.
Okay.
So that's the real gas law. And the two big take homes are that for one, I'm sorry, I'm really zoomed.
So we won't be doing any of these calculations.
No, I might have put one in the homework, or you might want to do one in the homework. But the two big take homes are this, that ideal gases are best at STP, and real gases, the pressure real
Right.
is, where's my notes? I want to go back to it. The real pressure is less than the ideal. And for the volume, the real volume is, I'd said that wrong. The real pressure is greater than the ideal. And the real volume is less than the ideal. And so
Okay.
those are two big take homes. But for the second take home, let's take a look at this van der Waals equation. So normally we have P times V equals nRT, right?
Right.
So what if we increase P and make it the real pressure, and that number gets bigger?
Yeah.
So here, let's pretend they're 10 and 10. What's 10 times 10?
100.
Okay, so now the real pressure is 11. Not 10, it's 11.
Right.
Oh my goodness, that's going to make all the difference in the world, right? But our real volume, we have to subtract a little bit. Let's subtract 1. 10 goes down to 9, right?
Right.
So now this is 11 and this is 9. What's 9 times, or 11 times 9?
99.
Okay, as opposed to 10 times 10, which is?
100.
So are they really that different?
No.
No. So these real gases are pretty much close to ideal gases. Now, I'm going to be honest, I gave you an exaggeration there about the differences. And sometimes the differences can result in more than just a 1% overall difference. It might result in as much as a 10% difference. But still, I would say that a 10% difference is pretty darn good. Okay. And again, I'm trying to convince you that in science, nothing is ever exact unless it's defined or counted. And we think we're doing a really good job if we're within 10% of the correct answer. And guess what happens if we find out that we can establish a better model?
And then we establish a better model.
We share it with people. And here's the problem with that is people go, well, so your old model was wrong, huh? And we say, no, it wasn't wrong. It was good, but this one's better. It's
Okay.
kind of like, buying a new car. Oh, so there was something wrong with your old car? No, it was just fine. But you know what? We wanted a better one. Now, that's not the way we buy cars in my family. We buy cars in my family because the old one dies. So the old one is really bad. We get a lot of use out of our cars. We're not one of those replace your car every 5 years family.
Probably a better way to be.
Yeah, we've got 299s, a 97, and a 2004.
What make are they?
The 4 is a Toyota. The 99s are Hondas, and the 97 is a Ford.
Mhm.
And we just take care of them.
Yeah.
If something goes wrong, we fix it. But also we do the regular maintenance. We don't just wait for something to break. So it's the same thing in science. When we get a new model, we share it. And there may not be nothing at all wrong with the old model. It's just not as good. Okay. All righty. So what would you like to do from here? Would you like to just look at some ideal gas problems?
Yeah, with whatever I need to be comfortable with.
Well, I don't know, to be honest. Let's take a look at, so here we have the 9 non-ideal gases.
Yeah.
So I'm going to zoom in on this, and this one we can just look at without really writing anything down more than likely.
Oh, I see.
Okay, let's look at number 51. Under which set of conditions will CO2 deviate most from ideal gas?
Well, not A.
Not A, that's ideal. Right?
Yeah.
So, and B, or actually C, is half ideal.
Yeah.
And D is half ideal, because at least the pressure's where you want it, right?
Right.
And B is neither is the ideal pressure or temp. So I'm going to have to say B is where it's going to deviate the most because it's not STP.
Yeah.
Okay. So that's pretty straightforward. Number 52.
Excuse me.
Gesundheit. Which will deviate. Now, we got to read this carefully. Deviate least.
Right.
So, in other words, be closest to ideal gas, right? It's like a double negative without putting any no's in there.
Mm-hmm.
Okay, so which one is going to deviate the least from ideal gas behavior?
A.
A, because those are the STP conditions. Fair enough? Okay. So here is one where you say, in the text, it is stated the pressure of 4 moles of chlorine in a 4-liter tank at 100 degrees Celsius should be 26 atmospheres if calculated use the van der Waals equation. Verify this result and compare it with the pressure predicted by the ideal gas law. So this is just a good exercise just to see what the real result would be versus the ideal gas law result. So let's go ahead and do this one, okay? So for number 53, and I'm too zoomed in. I want to try and capture the essence of the question here. The pressure of 4 moles in a 4-liter tank at 100 should be 26 atmospheres. And this is according to van der Waals for chlorine. So that's important that we know it's chlorine because we need to use the correct A's and B's, right?
Yeah.
Okay. And here we're supposed to also compare this to the ideal gas.
Okay.
So let's start off with the van der Waals by looking up the B's and the C's, or the A's and the B's, I'm sorry. And again, these are nothing you want to memorize. So for chlorine gas, the A for chlorine is 6.49 atmospheres, liters squared per mole squared. And the B for chlorine is 0.0562 liters per mole. So I'm actually including the units this time. So if we want to use the van der Waals equation, I'm going to rewrite it here. It's P plus A times N over V, that quantity squared, V minus Bn is equal to nRT. And here they say that we need to confirm that we want to verify this result. So we want to verify that we're going to get a P of 26 atmospheres. Now, this is the thing that I'm not quite sure. I think they mean this P right here.
Yeah.
Not this P. But they're not clear about it. You with me?
Yeah.
So we're going to calculate this P right here and see if it does end up being 26 atmospheres, okay? So I'm going to rewrite this as P plus A N over V squared is equal to nRT over V minus Bn. So you know how I got here, correct?
Yeah, divided.
So now I'm going to say nRT over V minus Bn, and I'm going to put minus A N over V squared.
Okay.
Because I'm just taking this and subtracting it from both sides.
Mm-hmm.
Okay, so now let's see what we get here. I'm not sure if I have enough room here, but I'm going to give it a shot. So we have N is 4 moles. R, I think for R, we want to use atmospheres because we want our answer to be in atmospheres, right?
Yeah.
So 0.08206 liters atmospheres per mole per K. And the temperature we can see is going to be 373.15 K. All of that divided by the volume, which is 4.00 liters, minus 0.0562 liters per mole, that's B, and 4.00 moles. So it looks to me like I need another parentheses here to make it all look correct. Now minus what?
A.
6.49 atmospheres liters squared over moles squared. That's A. And then I've kind of run out of room, so I'm going to write this up here, minus 6.49 atmospheres liters squared mole squared. That's A. N is 4 moles, right?
Yeah.
And V is 4 liters. Oh, I can see where they're going with this. They're doing us a favor here because you have 4 moles and 4 liters. What's 4 divided by 4?
1.
And 1 squared.
1.
1. So all of this is 1. We'll get moles squared and liters squared. So with the mole squares on top, what happens to the mole squares on the bottom over here?
1 cancels.
They both cancel because this is moles squared and moles squared.
Oh yeah.
And this is liters squared and liters squared. So what happens there?
Oh, those cancel too.
Right.
Well,
So
yeah.
we end up getting negative 6.49 atmospheres. You with me?
Yeah.
Okay, so here we know that that's minus 6.49 atmospheres without even touching the calculator. Now all we have to do is figure out what this is. And here's the estimate. What is 0.056 times 4? Now, the way I would do this is I would either do 5 times 4 is 20 or 6 times 4 is 24.
Right.
So maybe we make it 22. Now we know that 0.05 times 4 is not 22. It's got to be like 0.22 or 0.022 or something like that. What makes the most sense?
0.02.
Probably 0.02. So when we add that to, when we subtract that from 4, what do we get? 4 minus 0.02.
3.98.
No, it's 4. Come on. 3.98 versus 4. To say those are different is like to brag that, hey, I got $4. You only got $3.98. Ha ha.
Right.
You know, so let's say 4. Okay, so that's 4 on the bottom. Are you with me?
Mm-hmm.
Now on top we have 4 times all of this crap, and then divided by 4. What's 4 divided by 4?
1.
Okay, so basically we have 0.082 times 373. And the way we can do this is 1/10. 0.08 is 1/10. 1/10 of 37.3 is 37. But then we want to back down a bit because this is not 1/10. So instead of 37, we're going to say, well, minus like 5 or 6. So we'll call it 33.
Okay.
So we have 33 minus 6.49. What are we going to get?
26.
And that's what we should get, right?
Yeah.
They say we should get 26. So let's go ahead and do the calculations. Now, I'll be honest, with something like this, Charlotte, where it's this complex, I don't tend to put all of this in the calculator at once. I tend to do this stuff on the bottom first, then put it all together. So I'm going to do 0.0562 times 4. I'm going to subtract that from 4, and I get 3.7752. Okay.
Okay.
Now I'm going to go ahead and use all these numbers. I'm going to say 4 times 0.08206 times 373.15, and then divided by that 0.377 or whatever it was. And I get 32.444 atmospheres. Now,
I didn't get that.
what'd you get?
Negative 136.
Okay, did you do 4 times 0.08206 times
373.
373.15, and then divided by, what was that number? 3 point 77 something?
I don't know. I just did what we have written down.
Well, what was this number at the bottom?
I don't know. I didn't write it down.
Oh, well, we have to put that in there. So I got to recalculate that. 0.0562 times 4, and then minus 4, or subtract it from 4, I should say. So this on the bottom is 3.7752. So now I'm going to do 4 times 0.08206 times 373.15 and divided by that 3.7752. And I get 32.444.
Okay.
Now, this is going to be rounded to 3 zig figs because there's 4, so that we get 32.444. We round it to the 10th. Are you with me?
Yeah.
Now we subtract the 6.49 and we get 25.95 atmospheres, which we have to round to the 10th. So that becomes 26.0 atmospheres.
Nice.
Okay. So, and if we look at the units, can you see how the moles cancel here?
Yeah.
And here, these don't cancel because this is liters minus liters.
Okay. Not.
So they don't cancel, do they?
No.
Now, do you see how this mole cancels that mole?
Yes.
This K cancels this K?
Yep.
Well, on the bottom, since we have liters minus liters, the bottom will be liters, correct?
Yeah.
Now, that means that this liter on top is going to cancel with those liters on the bottom.
Both of them?
Well, absolutely, because remember, this is liter minus liter, which means the whole thing is liters. We could actually write
Okay.
4.00 liters minus 0.0562 liters per mole times 4. We could write this all as take the liters out here and put liters on the outside, right?
Yeah.
And that means that liter would cancel with that liter on the top. So yes, it cancels with both of them because they both are the same liter, as it were.
Okay.
Okay. So we do confirm that you get a pressure of 26 atmospheres.
Okay.
But the second part is, now let's calculate the pressure if we use the ideal gas law. Okay, so N is still 4.00 moles. That doesn't change. The temperature is still 373.15 K. That doesn't change. R, we're definitely going to use 0.08206 liters atmospheres mole K. And the reason we're going to use that R is because we want our answer in atmospheres and we'd like to be able to make the comparison. And the volume was 4.00 liters. So we're going to have P is equal to nRT over V. And let's just put in the values.
So I get 30.6.
Excellent. Did you estimate that before you did it in your calculator?
No.
Why not? Okay, 4 divided by 4 is?
1.
Okay, 0.082 times 37.3. Well, that's 1/10, so that means that answer is 37. And a very common way to do this is 0.08 is about 20% lower than 0.1.
Yeah.
So what's 10% of 37?
Um,
3.7.
yeah,
What's 20% of 37?
6,
Well, 3.7 twice, right?
yeah.
So
Uh,
7.2.
mhm,
So subtract 7.2 from 37, and what do you get?
30,
30. So the estimate is 30. What did you get for your answer?
30.6.
Okay, so this is using the ideal gas law. And the pressure we calculated using van der Waals was 26. They're within about, I would say, almost 10% of one another.
Mhm.
Okay. All right. Now, if you take a look at this, you might ask, so why are they so different? So what is the answer for why these are so different from one another?
Because the real pressure is higher than the ideal.
Well, the real pressure is, well, the pressure for either of them is really high, agreed?
Yeah,
Because the ideal pressure is 1 atmosphere. We're working at 30 times greater than the ideal pressure. What about the temp?
it's also a lot higher.
It's 100 degrees Celsius higher, or 100 K higher. Actually, I should say it's 100 K higher than the ideal temp, which is 273, right?
Yeah,
Okay. So why is this so far from, why is the 26 so far from the ideal of 30.6?
because it's not at STP.
Right. Because the pressure, whether you look at 26 or 30, that's a lot higher than 1.
Mhm.
And when you look at 373, that's a lot higher than 273. Okay, fair enough. So that's the kind of understanding I would like you to have from doing a problem like this is, yeah, going through all of the work here is, I get it, but we should understand why it's 10% off.
Okay,
And why is it 10% off?
because the STP was higher for both.
No, the STP is not higher for both. STP is 1 atmosphere and 0 degrees Celsius.
Right,
So what would you, let's be more clear. Because why?
because it was higher than STP.
Right.
It wasn't at STP.
So you could say, so the pressure was much higher than standard and the
Right.
temperature was much higher than standard. Fair enough?
Yeah.
All right. So I think that's enough with the ideal gases
Okay.
or non-ideal. I mean, if you take a look at the rest of these questions, can you see that basically they're giving you A's and B's and they're saying make some calculations.
Right.
Here, they have this one, which correction term has the greatest influence on the pressure of this system? A n over v squared or B times n. So you just calculate them and see which one has the greater influence. The one that has the greater influence is the one that changes the other value by the greater percentage.
Okay.
So these are just, here's some A's and B's, do some math. And I do understand the value of math, but I like the value of understanding it a little bit better. Okay, so we're done with non-ideal. What do you want to do next? Do you want to look at some diffusion or effusion problems, or do you want me to just do some problems from the back of the book?
Yeah.
Was that a yeah to diffusion and infusion, or problems from the back of the book?
Problems from the back.
Okay, so I don't want to repeat ones that I've already done. These are ones I haven't done yet. And the value in that is that if I don't do something I've done recently, you get to actually see how my brain thinks and how we want your brain to think. not a nice day today. Not here. It's overcast, but at least it's not raining. Okay, so this is number 72 on page 485. Analysis of a gaseous chlorofluorocarbon. And you can see why it's called a chlorofluorocarbon. It's got chlorine in it, fluorine in it, and carbon in it. Shows that it contains 11.79% carbon and 69.57% chlorine. Okay, and when they write these numbers out, they usually mean that is by mass. So if you think about 11.79 and 69.57, those clearly do not add up to 100%, do they?
No.
So what is the balance of this chlorofluorocarbon in that missing percentage? What element is that?
We're missing fluorine.
It's fluorine. Okay. So we have 11.79% carbon, 69.57% fluorine, and 100 minus 69.57 minus 11.79% fluorine. Fair enough?
Right.
I'm going to go ahead and calculate that real quick because I think we're going to need it, but I'm not sure. But I'm curious. What is the percentage going to be if we estimate it? Round that off. It's 70, isn't it?
Mm-hmm.
Round that off. It's 10, right?
Yeah.
So that's 80% there. So this should be around 20%, right?
Yeah.
And 18.64% is close to 20. Okay, in another experiment, you find that 0.107 grams of the compound fills a 454 milliliter flask at 25 degrees Celsius with a pressure of 21.3 millimeters of mercury. So what are the things that are standing out to you about this? To me, what stands out to me is that they gave me the volume in milliliters, those rotten, dirty people, when they know I want liters. They give me the temperature in 25 degrees Celsius, but I'm used to that. They're always doing that to me, so I'm going to add 273.
Right.
And get 298.15. So that one I'm used to. It's not a dirty, rotten trick. Now, the pressure, what am I thinking about the pressure?
Millimeters of mercury?
Yeah. Here's what I'm thinking. 760 is normal pressure, right?
Yeah.
This is really low compared to normal pressure.
Right.
So that means you have 21.33 millimeters of mercury pushing out, and you have 1 atmosphere pushing in. Does this container want to explode or implode?
Implode.
It wants to implode. So if you happen to drop this on the ground, it would implode, which looks like an explosion, except the sides go in. And if it were glass, the sides would go in and then bounce off of each other, right? So it looked like an explosion.
Yeah.
If this were a tin can and you started denting one side of the can would just go whoop and crumple, like just from looking at it. So these are the things that I think about when I'm looking at these numbers. I try and make them real to me. Fair enough?
Yeah.
Okay, so we want the molecular formula of the compound. So how do we normally get the molecular formula? We get the moles of carbon, we get the moles of fluorine, we get the moles of chlorine, right?
Right.
Okay, so how are we going to do this? Because I don't see how the moles of the gas, actually, I should say, I don't see how this percentage gives me the actual moles of chlorine. I
Could
guess it
we,
could. Oh, wait, yeah, it could. Can't we use the percentage of carbon to get the moles of carbon?
yeah,
We can say that, let's
Alright.
pretend we have 100 grams of the compound.
Right, each of them could be grams.
So that means we'd have 11.79 grams of carbon, wouldn't we?
Mhm.
Multiply by 1 mole of carbon per 12.01 grams of carbon. And we have the moles of carbon in 100 grams of the compound. So here we're assuming 100 grams of the compound. Now let's estimate this. What's 11.79 divided by 12.01?
It's almost 1.
Almost 1. And my calculator has 0.98168. And that's good to this 6 right here. And you're probably already on to fluorine or something, aren't you?
Chlorine?
Oh, I wrote this down wrong. Do you see that?
No, what'd you do? Oh, yeah.
What's 35.57 divided by 35 going to be?
1.
No, I said that wrong. What's 69.57 divided by 35.45?
Oh, almost 2.
More than 1, but less than 2, closer to 2. Definitely, I agree. 1.96. Yeah, that's really close to 2.
Don't we need, it's, oh, okay, it's not Cl2. I see.
No, it just says of the atom chlorine.
Yeah,
But,
I,
now that you've asked that, I want to show you something here because it wouldn't matter.
yeah, I know.
You started off with Cl2.
Right.
You would
Think
still
about-
get 1.9625 moles of chlorine atoms.
Yeah.
So we won't do that. So 18.64 grams of fluorine times 1 mole of fluorine per, I want to say 19.00, and it is. This is going to be really close to 1, isn't it?
Yeah.
And I bet you it's like 0.981.
Yeah.
How did I know that?
You've done it before?
Nope.
Okay.
It's so close to that number that I thought they've got to be the same moles, right?
Yeah.
Because it's a 1-to-1 ratio. So without too much effort, we can say, I'm just going to do this. C 0.98, chlorine 1.96, fluorine 0.98, comes out to chlorine 1, excuse me, carbon 1, chlorine 2, fluorine 1, which would be CCl2F. So that is the empirical formula. Now we want to find the molecular formula of this compound. How do we get the molecular formula of the compound? Usually we take the molar mass of the molecular formula, divide it by the molar mass of the empirical formula to get a multiplier, right?
Yeah,
What do
but
we don't have the molar mass.
yeah,
Oh, but wait, we've got grams. Whenever you see grams of the gas, what formula pops into your mind? D equals PM over RT.
right.
And D is M over V, lowercase m, right?
Yeah,
So we could calculate the molar mass if we have the pressure, if we have the temp, if we have the mass, and if we have the volume. Do we have those things?
right.
So we can calculate the molar mass here and then use this equation to get the multiplier.
Okay.
Okay. So I'm going to say that the molar mass, uppercase M, is equal to RT lowercase m divided by PV. Does that look good?
Yeah.
And up here, I'm going to do 458 milliliters times 1 liter per 1,000 milliliters is 0.458 liters.
Mhm.
So now we just do sort of a plug and chug. I'm imagining, since we're using millimeters of mercury, I want to use the R with millimeters of mercury, right?
Yeah.
So 62.37 liters, millimeters of mercury per mole per K. The temperature is 298.15 K. The mass is 0.107 grams. The pressure is 21.33 millimeters of mercury. And the volume is 0.458 liters. And I'm going to make sure the units cancel so that we get, hopefully, grams per mole. Yep, we get grams per mole. What's your estimate for this?
I'm still writing. I had to get another piece of paper.
Oh, okay.
Mm.
Have you estimated yet?
No. Um, so I was thinking 20 goes into 62 about 3 times.
Yep.
And then 3 times 300, 900.
Okay.
That's as far as I've gotten.
Well, what's 900 times 0.1?
90,
90 divided by a half.
45.
That's 90 divided by 2.
Oh, well, 90 divided by 0.5, is that right?
Yep.
I don't know. 450.
Nope. So how many times will half go into 90? Well, we
Well,
know
half,
one goes into 90 times, right?
yeah.
So half should go into 90 twice as many times.
Oh, okay.
So 180, right?
Yeah.
Now, let me show you another way to do this that might have made a little more sense, because no one likes dividing by a half. That sucks.
I mean, I guess.
But do you see that 0.458
Yeah.
is pretty close to half?
Yeah.
What's half times 21?
10.
10. Everyone loves dividing by 10.
Okay.
Okay, what's 10? What's 298 divided by 10? That's like saying, what's 300 divided by 10? It's 30. What's 30 times 1/10? 3. What's 3 times 62? 180, 190.
Okay.
And so you see, by doing it a different way, you still get about 180, 190. You with me?
Yeah.
Okay, so if we know the molar mass is about 190, and we know this has a molar mass of 12 plus 71 plus 19, which totals about 100 or 95. Actually, that's going to be 102, right? So if we know this number is about 180 and that's 102, this number is probably going to be closer to 200, right?
Yeah.
Because 200 divided by 100 means the multiplier is 2. But let's go ahead and carry on and make sure that we're on the right track. So I'm thinking that the formula is going to be C2Cl4F2. What do you think?
Sure.
Doesn't it make sense?
Yeah.
Okay, well, let's figure it out. 62.37 times 298.15 times 0.107 divided by 21.33 divided by 0.458, and it's 203.67 or 68. I'm going to round. So here, 12 plus 71 plus 19 is 102. So we're going to get, for the multiplier, we're going to get 204 divided by 102 is 2. I rounded that to 204. That's 102. And boom, we now get CCl2F, 2 of them, becomes C2Cl4F4. And that is the molecular formula. So, quick question. Why is that? Oh, that's supposed to be a 2 on the fluorine, not a 4. So, quick question here. Why is this formula I have written here that I'm pointing at, why is that a molecular formula and not an empirical formula?
Because it's the actual formula.
Okay, but what is the empirical formula supposed to be?
I want to say like the simplified.
Simplest ratio of elements. That's it.
Okay.
And so I would say this is not an empirical formula because it's not the simplest ratio.
Okay. Yeah.
Okay? So if the question is, why is that not the empirical formula? Well, it's because it's not the simplest ratio.
Okay.
If the question is, why is that the molecular formula? The answer would be, well, because the molecule has exactly 2 carbon atoms, exactly 4 chlorine atoms, and exactly 2 fluorine atoms.
Right.
Okay. Because the big difference is empirical formula is simplest ratio. Molecular formula is actual number of each element. Okay, excellent. Okay, what number was that?
72.
Okay, that one's done.
Are we doing?
We're doing
74?
80. We're skipping to 80.
Oh,
Yeah, I'm not doing every other one. There's so many problems in this chapter that I just picked a few to do.
yeah, there are a lot.
There are a lot. Okay, considering the following gases: helium, sulfur dioxide, carbon dioxide, and chlorine, which has the largest density, assuming that all gases are at the same temperature and pressure? So what equation do we probably want to use?
D equals PM over RT.
Now, they all have the same pressure, they all have the same temp, and they all have the same R, right?
Yeah.
So couldn't we say, I'm going to rewrite this as D is equal to M times P over RT. Now, why did I write them this way? I wrote that this way because it doesn't matter what the gas is, PRT is the same.
Okay.
So what is going to determine how large the density is?
Molar mass.
The molar mass. So A, we simply look at which one has the larger molar mass. So let's look at each of these. Helium is 4.01. SO2 is 1 sulfur, which is 32, plus 2 oxygens, which would be another 32, so that's 64. And look, I'm not even getting the molar mass precisely, because if they're very different, that's all I need to know. What's CO2? How much is a carbon?
12.
How much is 2 oxygens?
32.
Add those together.
46.
44.
44.
Even if you figured 46, it wouldn't change the answer.
Right.
A chlorine is 35 and a half. 2 of those would be 71, right?
Yeah.
Ish. Okay, so we just have to answer which has the largest density.
Right. So chlorine gas.
Cl2 has the largest density. What if we were asked, put these in order from smallest density to highest density? What would we do?
Right. And how they are.
No,
Well, I mean, just that order, that same order.
no.
Why not? Oh, I see. So helium or sulfur, carbon dioxide.
Getting a little too overconfident there.
Yeah, I wasn't looking at it.
Okay, which will
Okay.
effuse the fastest? Well, remember the rate of effusion is equal to the square root of 3 RT over the molar mass.
Right.
So which one effuses faster? Large molar mass or small molar mass?
Small.
Small molar mass effuses faster. So that would be helium. So what if I asked you to put them in the rate of which one effuses slower to which one effuses faster? What would we write down? Beginning with the slowest.
Chlorine.
Okay, the next slowest.
Sulfur dioxide. I don't know.
Right, that's how you say it. That's how you name it. Good. Next one.
Carbon dioxide.
Excellent. And the one that effuses the fastest, so it's got the greater sign.
Helium.
Okay, so kind of the take home on this one, which was what, number
80.
80. I think the take home on this one was, you know what? Whenever they start giving you grams of gas, you better start thinking about that density equation. It might be useful.
Right.
Okay. It may not be useful, but it might be the answer to solving the problem. Okay, here's number 84. In an experiment, you have determined that 0.66 moles of CF4 effuse through a porous barrier over a 4.8 minute period. How long will it take for 0.66 moles of CH4 to effuse through the same barrier? Okay, so can you see that we're looking at the same amount of each?
Yeah.
Okay, can you see that CF4 has a much larger molar mass than CH4 because each fluorine weighs 19, whereas here each hydrogen weighs 1.
Right.
So we would think that the CH4 should effuse faster than 4.8 minutes.
Yeah.
Okay, so whatever happens here, we should get an answer of greater, or excuse me, smaller than 4.8 minutes.
Yeah.
So if I remember right, it's the rate of A over the rate of B is equal to the molar mass of B over the molar mass of A. And the rate, well, I'm just going to leave that there. Okay, so I think that maybe we want to say that CH4 is going to be the rate of A, because that seems like what we're kind of solving for, right?
Yeah.
So let's figure out the molar masses of each of these. So CH4 is going to be 12.01 plus 4.04 for 16.05. CF4 is going to be 12.01 plus 19 times 4. And the way I do that is 20 times 4 is 80. So 19 times 4 is 76. Twelve plus 76 is 86.01.
88.
Thank you. Good job.
I used my calculator.
Ah. Okay, now how do you want me to set this up?
Well, we're gonna plug in the molar masses of each.
Right, but what do you want me to use for the rate of A and the rate of B? The rate of A we don't have because that's CH4, right?
Right.
I'm going to put rate CH4. I'll start it this way. Rate of CF4 is equal to the molar mass of CF4 over the molar mass of CH4. So does this make sense given what we have in this problem?
Yeah.
Okay, so how do you want me to manipulate this?
So we need to isolate the rate of CH4.
Okay.
So we're going to multiply each side by CF4.
Okay. Now I'm going to use parentheses here because I don't like this radical here, or whatever you call it. You know, you don't know where it ends, right? And I remember back in the day, what we used to do is we used to like put that there. So that meant, hey, that's the end of it.
Oh, okay.
Because if you don't do that, you don't know if this belongs underneath there or not.
Okay.
Okay,
So
so now what do you want me to do here?
we plug in what we know.
Okay, so what is the molar mass of CF4?
88.01 grams.
I'm going to put grams per mole. And CH4?
16.05 grams per mole.
So naturally the grams per mole cancel and we have 88 divided by 16.
Right.
And doesn't 16 go into 88, what, 5 times roughly?
Um, I think so.
So we're going to have the square root of 5, which I don't like. But I know that square root of 4 is 2.
Right.
I know the square root of 9 is 3. So I figured the square root of this has got to be closer to 2 than 3. So 2.25.
Okay.
What are we going to write down for the rate of CF4?
So is it 4.8 minutes per mole? Or
The other way around,
4.8 moles per minute makes more sense.
right? Don't we, for rate, don't we say per hour or per minute?
Yeah.
So how many minutes was it? 4.8 minutes.
Yeah.
Did a whole mole fuse in that amount of time?
No.
How much did?
Oh, 0.66 moles.
Okay, so you're right on track, except we want to say 0.66 moles.
Okay.
Are you with me there?
Yep.
Okay, excellent job. So naturally, if on the inside it's 2.25, how many times does 2.25 go into 4.8?
A lot.
How about twice?
Yeah.
And what's
Okay,
2 into 0.66?
Huh?
What's 2 into 0.66? Or 0.66 divided by 2?
1.
0.66 divided by 2.
Oh, so it's going to be smaller. So
0.33.
0.3, yeah, 0.33.
And we said that it should be, that's 0.33 moles per minute, right?
Yeah.
And here's what I'm going to do is I'm going to leave this alone and not mess with it. Because when I take all of this and do that work, I will find out, actually, let's forget what I just said there. Let's just figure out how many moles per minute. And we just said it's about 0.33, right?
Yeah.
So let's do the work and calculate it. For my calculator, I have to put square root in before I start this problem. Okay, and here's a problem that I just found out. I just did square root, and then I said 88.01 divided by 16.05, right?
Yeah.
And we said that answer should come out to be like between 2 and 3, but closer to 2.
Yeah.
My calculator says 0.06.
Uh-oh.
So when I did this on my calculator, I did square root of 88, which it did for me. The square root of 88 is like 9. 9 times 9 is 81.
Mm-hmm.
And then it did 9 divided by 16. So I got to change that. So I got to do square root parentheses 88.01 divided by 16.05 and parentheses, and I'd better get around 2.25 is what we said. And that didn't work either. I just want to make sure that this came out really funky. and my answer is 1. So none of that's working for my calculator. What should I do?
I don't know. I got,
I'll tell you what I'm going to do. I'm going to take 88.06 and divide it by 16.05.
did you put parentheses after 16.05?
I don't know. I usually don't put end parentheses on because the calculator understands that.
Well, that's what I did. Try it.
And did it work for you?
Yeah. And then parentheses.
Oh, actually, it didn't work for me. I got 5.48. Oh, I had to put equal twice. I get 1.36.
You do?
Got,
No, I got 0.32.
oh, I'm sorry. I get 1.3639 for all of this stuff.
Oh, on that one side. Okay.
Yeah. And remember, our estimate was 0.33. So when you got 0.32, how did that make you feel? Actually, I didn't get that. I get 0.18.
Not what I got. Weird. Let me see your calculator.
Oh, it shouldn't be 1.36. That's just wrong. Okay, so I'm going to do the square root of 5.4834. Wow, my calculator is funky. Check this out. So that's square root, right?
Mm-hmm.
Square root of 4 should be 2. Why does it have this answer here? I'm going to turn my calculator off. That way it'll forget everything. Turn it back on. And now I'm going to do the square root of 4. Look, it's always multiplying the answer. What is that? I have somehow or other programmed my calculator. Oh, I know what I'm doing. Excuse me. Now that I look at this more closely, do you see the caret?
No.
That says X root. Do you see the
Oh,
X squared? That's square. I've been pushing the wrong button. So square root, let's try this, 88.01 divided by 16.05, 2.34, which seems about right, times 0.66 and divided by 4.8, 0.32. And here we're looking at 2 zig figs, and that's moles per minute, right?
right.
Okay, now the question, if we go back to it, if I can find it, is not what is the rate, but how long will it take?
Oh, okay.
So to finish this problem off, we need to take our 0.66 moles and multiply it by 1 minute per 0.32 moles. So I have taken this 0.32 moles and flipped it.
Okay.
Why did I flip it?
Because it's equal, it's the same.
So that the
Value.
moles cancel.
Yeah.
So take our 0.66 and divide it by 0.32 and we get 2.1 minutes. And remember, we said that since CH4 has a smaller molar mass, it should diffuse faster than CF4, which took 4.8 minutes.
Right. So it is a lot faster.
So one of the things that may confuse you, though, is that one of these took 4.8 minutes, and the other took 2.1 minutes. And you could argue that 2.1 is almost half of 4.8.
Yeah.
So it diffuses twice as fast,
Right.
but the molar mass is 5 times smaller. That
Yeah,
seems
so
kind of weird, doesn't it?
they're not proportional.
It's not directly proportional. It's proportional to the square root. That's why.
Okay.
So that's what's going on there. So instead of twice, or instead of half as much, it's not quite there. So I guess the thing I want to say is that when you look at 4.8 and 2.1, they're not as different as the molar masses, and they're not as different as the molar masses because we have the square root in here. Okay. All right. Which one was that? 84?
Yeah.
You still have time, or do you want to call it quits?
Want to do one more?
Oh, we can. It's up to you.
I'm getting hungry.
Me too. Why don't you cook something and send it on down to me?
I need to go grocery shopping.
Yeah. If you have a sample of water in a closed container, some of the water will evaporate until the pressure of the water vapor at 25 degrees Celsius is 23.8 millimeters of mercury. How many molecules of water per cubic centimeter exist in the vapor phase?
So it's asking for N, like an amount.
Yeah.
Right?
So we definitely want to know N. And we want to know per cubic centimeter. So isn't that like a volume or per milliliter?
Yeah.
And let's actually draw this, okay? So here's my closed container. And the reason you know it's closed is because the lid is on. There's the lid. And we put water in here. And there is air in here. I mean, you can't put water in a container without air. Fair enough?
Yeah.
And we're assuming that the air has no water molecules in it whatsoever. So it's what we would call dry air.
Hmm.
So are we still going to have air in our closed container? Absolutely. But now we're going to have some water molecules in here. And what happens is when this goes from here to here, water molecules come out and become gas, but also water molecules go back in and become water until we have equilibrium.
Yeah.
And the overall pressure is 23.8 millimeters of mercury.
Mm-hmm.
Now, this is what we call the vapor pressure of water.
Okay.
So it's really the pressure of the gas molecules of H2O.
Okay.
And this vapor pressure depends on whether you live in a dry environment or a wet environment. Okay, so that's what's happening. And this is a 25.0 degrees Celsius, which is 298.15 K. And we want to know the number of molecules of H2O per 1 centimeter cubed, which is the same as saying the number of molecules of H2O per 1 milliliter.
Yeah.
Now, I'm a little bit leery of that milliliter. Why is that?
Because you normally work with liters.
Right. So what I'm going to do is I'm going to multiply by 1,000 milliliters over 1 liter and get, we want to know
So
1,000 times the number of molecules per liter. For this number of molecules, I'm going to use the letter X.
X molecules.
So 1,000 times X molecules of H2O per 1 liter.
Okay.
And I don't like this 1,000 times X. So you know what I'm going to call that? I'm going to call that Z. I want to know how many molecules per liter. Because here's the idea. If I know there's 1,000 molecules per liter, how many are there per 1 milliliter?
10,000?
If I have 1,000 per liter,
Mm-hmm.
how many in 1 milliliter?
Oh, point.
1.
Oh, yeah.
Because there's 1,000 milliliters in a liter. So that means if you have 1,000 in there, it's 1 per milliliter. If you have 2,000 molecules, the idea here is that I can figure it out.
Great.
I can figure it out later. But since I want to work with liters, I'm going to say, hey, I want to figure out how many molecules per liter. Then I'll figure out how many per milliliter.
Okay.
Fair enough? But we don't have a idea of how to calculate the molecules per, we don't have an idea of how to calculate the molecules per liter, do we?
No.
But think about molecules per liter. What does that remind you of as far as a physical property? Something per liter.
Molarity.
Yes, but this is not a solution, so we don't want to do that. So think about gases, something per liter.
I don't know. Density?
Density is per liter, isn't it?
Yeah.
But it's not molecules per liter, or moles per liter, it's grams per liter.
Right.
So you know what I'm thinking? What if we use this? If we could figure out how many grams per liter, if we could figure out grams per liter, we could figure out molecules per liter. Then we could figure out molecules per milliliter. Does that seem reasonable?
Yeah.
How do we go from grams to molecules? Sounds like we should do this instead. From grams to liters, we go to moles per liter. Then we go to molecules per liter. And then we go molecules to milliliter. So I think we've got a good idea of how we want to approach this. So let's calculate the density The pressure is 23.8 millimeters of mercury. The molar mass of H2O is 16 plus 2.01, which is 18.02 grams per mole. I think for the R, we want to use the one with millimeters of mercury, right?
Yeah.
And the temperature is 298.15 K. And this is going to give us our density of water. Are you ready to estimate this one?
Almost.
It's a tough one. So here's the shot I gave at it. 23 goes into 62 how many times?
3.
So I'm going to say 1 over 3. 18 goes into 298 how many times?
10.
Uh,
Or more than 10.
yeah, I'd say 1 over 15. So this is equal to 1 over 45, right?
Yeah.
Which is like 1 over 50, which is about 0.02.
Oh, that's what I got.
So when I put this into my calculator, I don't get 0.02. I get 0.023, so I'm pretty happy.
I was off on a decimal.
What's important though is that you may be off by decimal, but you kind of got the beginning numbers correct. So that should give you some sort of confidence in your answer, okay?
Mhm. Okay.
Okay, so what are the units here?
Grams per mole.
No, don't the moles cancel?
Oh yeah,
And don't the K's cancel?
right.
And the grams do not cancel.
So,
But in the bottom, the liters don't cancel.
oh yeah, that's what we wanted to.
So we got grams per liter, and now we're going to go on the grand journey of getting molecules per milliliter. So I'm going to write 0.02306 grams per liter times 1 mole per 18.02 grams times 6.022 times 10 to the 23rd molecules per mole, and then times 1 liter per 1,000 milliliters. Oh my goodness. I don't know if I did that right.
That's what I got.
7.71 times 10 to the 17th molecules per milliliter.
Mm-hmm. Is that a lot? I mean,
Well, what do you think?
well, yeah, it sounds like a lot, but are you thinking it's more than it
That's a
should be?
lot. And that's just in the vapor. Just think how many molecules of water there are in water. It's got to be a lot bigger than this, right?
Yeah.
And I happen to know that the density of water is 55 moles per liter. That's the density of water. So times 6.022 times 10 to the 23rd molecules per 1 mole, and then times 1 liter per 1,000 milliliters. So as a comparison, I don't know why I'm doing this. 55 times 6 is 300, right? 300 times 10 to the 23rd, and this is really times 10 to the 20. So we get 300 times 10 to the 20, which is equal to 3 times 10 to the 22 molecules per milliliter. So this number here, the way you look at it is that that's 5 different, right? 22 over 17, 5 different.
Yeah.
So 5 different is 5 zeros. 5 zeros is what? 100,000 times different.
Okay.
So there's 100,000 times more molecules of water per milliliter than there are molecules of water in the vapor. And that makes you think that water is really dense, doesn't it?
Yeah.
And it is. That's why when you jump off the Golden Gate Bridge, you don't want to hit it. Water's too dense.
Yeah.
And actually, that means that when you jump off the high dive 30 feet, that's why that water hurts if you don't land right. It's dense. Do you swim?
Yeah.
Okay. So then you've probably gone off a high dive, right?
No.
It's scary. I mean, you see people do it, and then you climb up the ladder and you get up there and you look down and you see that the people look like the size of ants, and you're like, nope, I'm just climbing back down. And then your friend shoves you over and you're like, ah, and it kind of sucks.
I like swimming in the river more, jumping off the rocks.
We in Colorado never swam in rivers because the rivers were snow melt. And so the water was really cold, but the reservoirs would warm up.
Yeah.
And so we would jump off the rocks into the reservoir.
Yeah.
And go swimming. And that was a lot of fun. All right. Well, we did a good job today. Thanks for calling in. I will post this later today if I can remember.
Okay.
We'll see you tomorrow, okay?
Alrighty. Thank you.
You have a good day and have a good lunch.
You too. Bye.